All right, now I know that you are ready for a more complex example of equivalent resistance, so let's try this one on for size. Don't let it intimidate you, it's going to be just fine. So once again, our first step is always just to draw all the different pathways that current can take through this circuit. And so if I follow from the high potential side of the battery, all the current's going to go through this 20 ohm resistor, but then some will go down through this 40 ohm resistor and then back up to the battery. Some of it will keep going through, go through the 8 ohm resistor, down through a 40, through a 12, and back up. And some of it will keep going all the way through, still through the 8 ohm resistor, but now through this other 40 ohm resistor, through the 12, and back up again. All right, so there are 3 different current pathways that I'm seeing here. And I also see 2 different places where the current is getting split up. All right, I see that one place where the current is splitting is right here. This is where the green splits off from the purple and the blue. And then the green, purple, and blue all reunite down here. So this is one place where I see currents splitting off in parallel and coming back together. Another place where I see that happening is over here. This is the place where I see the purple and the blue splitting apart, and here's where they come back together. So in this situation, I've got a parallel within a parallel. And so in terms of choosing which one to condense down first, always go with the simpler one. I could start with the red one, but then that one's kind of a pain because then I've got these weird resistors that are like in series and then more parallels, and like that's kind of a nightmare. Whereas if I just look at the blue section right here and ignore everything else, like, oh, that's kind of nice and easy. So I'm going to focus in on this blue parallel section first. All right, now before I can add branches in parallel, I need to make sure that there's only one resistor on each branch of that parallel section. All right, only one resistor on each path between the 2 dots here. And the good news is I'm already there. So whether I go down this way, it's just one 40 ohm resistor, or whether I go around that way, it's just one 40 ohm resistor. So I'm ready to go ahead and add those 2 in parallel with each other. So 1 over equivalent resistance, since these are in parallel, is equal to 1 over 40 plus 1 over 40. And I can go through and solve all of that, but a little quick tip for you is anytime you've got 2 identical resistors in parallel, the equivalent resistance is just half of each one's original resistance, okay? So this will end up just being 20 ohms. So now I'm gonna go ahead and redraw my circuit, collapsing those 2 parallel sections down into just one 20 ohm resistor. So that's a 20, a 40, an 8, a 12, and now that whole section has been replaced by a 20 ohm resistor. So now I've collapsed one of my parallel sections. I still have one more parallel section that I want to collapse down, all right? And so once again, I need to make sure that there's only one resistor on each of those pathways between the 2 dots here. All right, now along this pathway, I'm fine. I just have the 140 ohm resistor, but along this pathway, there are 3 resistors that I have to pass through. But the good news is what I can see is that these 3 are all in series with each other. Any current that goes through the 8 ohm resistor has to go through the 20 and the 12 as well. So before I go adding anything in parallel, I'm going to add these 3 resistors together in series first. So the equivalent resistance on that branch then is going to be equal to just the sum of them. 8 ohms plus 20 ohms plus 12 ohms, which is equal to, well, 40 ohms. Sorry, you couldn't see that. My bad. All right. So yeah, so the equivalent resistance of that whole section is just the sum of all of those resistors that are in series, which is 40 ohms. Now I'm going to redraw my circuit again. And then for this branch, I've now combined all of those into a single 40 ohm resistor. All right, so now I still have this parallel section that I want to condense down, but now I'm ready to do that because each pathway from the junction to the other junction has only one resistor on it, whether I go this way or I go that way. So I'm going to go ahead and combine those two together now in parallel. So that's 1 over equivalent resistance is equal to 1 over 40 plus 1 over 40. And again, as we mentioned before, anytime you've got two resistors that are identical in parallel with each other, the equivalent resistance is just going to be half of what each resistor's original resistance was. So those are going to combine to a single 20 ohm resistor. All right, one more redraw here. So my 20 ohm resistor stays the same. This whole parallel section just collapses down to a single pathway with a resistor of 20 ohms on it. And then these two resistors are just in series. So all I have to do now, whoa, that's not a cue, whatever, you know what, it's fine. I just add them together. 20 ohms plus 20 ohms gives me a total equivalent resistance of 40 ohms for the entire circuit, which means that this circuit up here, our original one, draws the same amount of current from our battery as just a single 40 ohm resistor would have, right? I hope that clarifies a little bit about equivalent resistance for you. A couple reminders with that. Number one, always start with your parallel sections. Number two, you can't add things in parallel until you only have one resistor on each branch. Number three, never ever add resistors in series if there is a junction between them. You can only add resistors in series if they share all of the same current. And number four, don't be lazy, redraw the circuit. That's going to be really, really important when we get to our next and final lesson for the unit. All right, good luck. Hope it goes well.